Okay, let me share video. Okay, so in the previous video, we considered a cyclic process with this light clock. And so we have Bob. So Bob is on the ground. Okay, and he is observing Alice. So Bob has his own light clock, okay? And he's observing Alice's light clock. So this is Alice. And doing this observation, he says, well, Bob says, the time according to his clock that it took for Alice up and down cycle is 2d over c, and 1 minus d over c quantity squared. Okay, and Alice, the time that it took for my up and down cycle, according to her clock, okay, is 2d over c. So we call this delta t, call this delta t prime, and so we see that delta t is really delta t prime divided by 1 minus v over c squared taking square root, okay? And so let's remind ourselves what delta t and delta t prime means. Delta t prime was the time between two events in a frame at which the events took place at the same location. The two events don't have to be one cycle, the beginning and the end of a light cycle. It could be the time that it took for Alice to eat a sandwich. Okay, it could have been 1 trillion light cycles, but okay, so that would be delta t prime. And according to Bob, it would be 1 trillion light cycles times this extra factor, okay? By the way, since we're at it, this factor, it appears in relativity very often. It's called a gamma factor. So we can say that delta t equals gamma delta t prime, and gamma is always bigger than or equal to 1. And it's all gamma equal 1 if v equals 0. You can see if v equals 0, then gamma is 1. Otherwise, it's always bigger than 1 because v is less than c. So the denominator is less than 1. So 1 over that is bigger than 1. Okay, so if it took 1 trillion cycles for Alice, so delta t in the number of cycles is 1 trillion. In Bob's clock, the time that it took for Alice to eat a sandwich was maybe 1.5 trillion cycles. So it doesn't have to be just one cycle. So let's remind ourselves what exactly is delta t and delta t prime. So delta t prime equals time between two events in a frame in which those two events took place at the same location. So I already emphasized. So that's delta t prime. And delta t, okay, is a time interval. Oh yeah, and by the way, I already emphasized that the two events only separate by time in this frame. Okay. Okay. Delta t um, was the time. Oh yeah, and let me while we're at it, there is an important concept in relativity, an important term um, called proper time. The time interval between events that take place at the same location is called proper time. And some books prefer to use the letter tau. Okay, so delta t, so delta t prime, I'm sorry, equals tau. I'm just going to use tau. Okay. On the other hand, delta t was the time interval or time between the same two events as measured in a frame in which the two events were not at the same location. So according to that frame, the two events were separated not only by time, but also by space. Okay. Remember, the light was emitted here, but it was absorbed here, as seen by Bob. Okay. So another way to interpret our result, that delta t equals gamma delta t prime, or sorry, I'm now going to use tau, proper tau. Another way to interpret this result, that delta t equals the gamma factor, which is bigger than 1, times the proper time, the time interval measured from the frame in which the events took place at the same location. So another way to interpret this is that the time interval between two events is always larger than when measured in a frame in which the events took place at the same location. okay? And it's only equal when the two events took place at the same location according to both frames, okay? Equivalently, the time interval between the two events is always greater than or equal to the proper time. It is only equal to the proper time if the frame in which the events took place, it's only equal to the proper time in the frame in which the two events took place at the same location, okay? And if it happens in two frames, the two frames are just translated by space. In other words, here's frame 1, and here's frame 2, and frame 2 is not moving relative to frame 1. In that case, in both frames, the time measured would be the same, and it would be the proper time. So again, what this difference in time intervals means is, it means, for instance, that while the light clock on spaceship goes through one cycle, okay, one up and down cycle, the light clock on the ground, remember ground has its own light clock on the ground goes through more than one cycle, okay? Or while there are two events that when timed on the spaceship took 1 trillion cycles, the clock that's located on the ground would say no. Well, according to the clock on the ground, we would measure that it took 1.5 trillion cycles, starting to eat a sandwich and ending, finishing the sandwich. So this is an interesting effect. And again, it's called time dilation. How big is this effect? Well, remember, delta t equals gamma tau, okay? And gamma equals 1 over 1 minus v over c squared, okay? Let's say the spaceship is the spaceships that we have right now, International Space Station. How fast does the International Space Station? International Space Station, that's about I looked it up, 660 meters per second. Now speed of light is about 3 times 10 to the 8 meters per second. Now this seems fast, but in comparison to speed of light, it's snail space. Okay, so now, so from this we see that v over c equals about 2.53. Let's see, 1, 2, 3, 4, 5 times 10 to the minus 5. It's a unitless number. It's a ratio of speeds. So gamma comes out to be 1 plus 3.6 times 10 to the minus 10. Okay? So gamma is extremely close to 1. Okay? So that's 1 in 10 billion. So that means if you have a clock that ticks at 10 billion oscillations per second, every 10 billion or 30 billion really, cycles, the two clocks will be off by 1 cycle. Okay? It's a very small effect. And International Space Station is pretty fast in comparison to what we're used to on Earth. Almost everything else is slower. And so it's not surprising that we don't notice this effect. So that's an interesting point. Second point, you might wonder, well, we use the light clock here, but how do we know that this effect does not depend on the mechanism of a clock? What's the big brouhaha about the light clock? Why did you start with that? Let's say there is another type of clock. Let's say you synchronize this new clock, the new model, that you think when you give that clock to Alice, it will not appear to slow down. Okay, so let's say there is a new model. Okay, so then when the light clock goes through, let's say when the light clock goes through a cycle, it does some physical act. Let's say it throws a tomato against the wall. Okay? And when the new clock goes through a cycle, it does some other physical act. For example, it explodes a packet of confetti. So you have your light clock, the tomato throwing light clock. You give a replica to Alice, okay? And then you give her the new model that throws the confetti. Okay, my point is that both do something physical. Okay, so you give the light clock that throws the tomato to Alice, and you also give her the new model. Okay, so you put those two clocks on the spaceship while you retain your own light clock, and then you observe the light clock on the spaceship, which we just argued appears to run slow, and the new model. And you're saying, well, the new model is not going to run slow. I can outsmart this. So is it possible? Is it possible that while the light clock on the ship runs slower than the light clock in your frame, as we just discussed, which is really a consequence of the second postulate, that the new model on the spaceship runs just as fast as the one on the ground? Okay, so let's say we're timing an interval between the two events, the time that it takes for Alice to do her homework problem. Okay, okay, so according to Alice, it takes 30 minutes. Okay, so when she's on the ground, it takes 30 minutes. When she's on the spaceship, according to her, it takes 30 minutes. If she's judging it based on the light clock. Okay, so let's say the point is, let's say she's timing some process, like doing homework, or some other process. So let's say, just for the sake of numbers, while the light clock goes through 10 cycles, it throws 10 tomatoes, the new model now emits, goes through 20 cycles, it emits 20 packets of confetti. Okay, and of course the light on the ground also throws 20 tomatoes. Okay, so when everyone was on the ground, if one clock goes through 20 cycles, another goes through 20. But now she's on a spaceship, while the clock on the ground throws 20 tomatoes, her light clock throws 10 tomatoes, but the new model, the one that throws confetti, still emits 20 packets. It doesn't look like it has slowed down. Okay, now she's on a spaceship and she sees two clocks. One threw 10 tomatoes against the wall, the other emitted 20 packets of confetti. But when she was on the ground, both emitted equal number of objects. So what that means is that the person in the spaceship will see 10 tomatoes thrown during the interval when 20 packets of confetti were emitted. So what does it mean? It means that without looking outside, she can tell how fast she's moving. Because when she wasn't moving, relative to Bob, both clocks emitted equal number of objects. In other words, this idea that you can outsmart the time dilation effect by inventing some new clock, it predicts absolute motion, which violates principle of relativity. And it would be absolute motion relative to Bob. Somehow Bob's frame is special. When you're at rest relative to Bob, both models tick at the same rate. But when you're not at rest relative to Bob, then they don't tick at the same rate, okay? So that's clearly nonsense. It violates principle of relativity. So what does it really mean? Okay, this leads to a very profound conclusion. If the proper time interval is always less than the time interval measured in another frame, regardless of the machinery of the clock that measured that time interval, then it's not about clocks. It's about time itself. It's not about clocks. Time itself appears to be running slower on spaceship than on the ground. me put that down. Okay, so it's not about clocks. During one tick of a clock on the wall of a spaceship, the clock on the wall of the ground makes more ticks, say 1.5 ticks or 2 ticks. And it's not about clocks. Everything appears to be slowed down on the spaceship. A person brushing teeth on the spaceship appears to move their hand slowly. While they're brushing their teeth, while moving the spaceship, so while they're brushing their teeth, you have the time to take a shower, go for a run, eat breakfast, and do a couple of problems on the home. They appear to do everything slowly. Their heartbeat seems slow, their blinking seems slow, the flame of their candles seems to flutter slowly, and so on. All physical processes on a spaceship, according to you, unfold slower than the same kinds of processes in your frame. Very important to note that the person on the spaceship doesn't feel slow. Okay? As your textbook emphasizes, you always feel normal in your own reference frame. So I have my own reference frame attached to me. I'm not moving relative to that reference frame. In my own reference frame, I don't feel slow. Okay, I will come back to that point. But perhaps there is something itching in the back of your mind, and I will even tell you what it is. That will be the subject of the next portion. You're probably thinking, well, if Bob thinks that Alice is doing everything slowly, wouldn't Alice think the same thing about Bob? Because according to Alice, she's not moving, and Bob is the one who's moving in the opposite direction, but it doesn't matter. The directionality isn't part of the effect. So how do you resolve that paradox? It's not a paradox, and we will resolve it in the third video. We will discuss that in the third video.